Good morning, good afternoon, good evening, everyone, wherever you are in the world. I am honored to welcome you to the third session of TDK Ventures Energy Week 2021 conference, covering topics related to energy transformation, or like we like to call it, EX. For those of you who joined the first two sessions, welcome back. My name is Nicolas Sauvage. I'm the president of TDK Ventures, the corporate venture capital arm of the Japanese electronic giant TDK Corporation. We care about energy transformation, and we made 18 investments in deep tech companies in a little more than 2 years, many in the energy, mobility, and material science spaces, all relevant to EX. I will be moderating our session today. Like every other sessions in Energy Week, we designed our panel to be with thought leaders representing academia, industry, entrepreneurs, and the investment community. We feel strongly about the diversity in each panel. We believe this is what will give us an opportunity for real, meaningful actions. Today, I am excited to introduce our amazing panelists and really looking forward to a stimulating and hopefully thought-provoking conversation. Our first panelist is an amazing academic and entrepreneur, Clare Grey, the award-winning chemist and professor from Cambridge University, also co-founder of Nyobolt, a startup providing ultra-fast charging technology. Our second panelist is Ping Liu, a distinguished pioneer and inventor in the energy field, with over 70 peer-reviewed published papers and over 36 patents in batteries, fuel cells, and more. He was program director at ARPA-E, managing research programs in energy storage for EVs. Our third panelist is Cindy Choi, investor and managing director at the corporate VC Total Energies Ventures. And she's on the board of Tado, Octillion, Sunfire, Deep Branch, Solstice, Level 10 Energy, and Autogrid. She was also head of corporate development at SunPower. Our fourth panelist is Doron Myersdorf, entrepreneur, co-founder, and CEO of StoreDot, pioneer and leader of extreme fast charging battery technology for electric vehicles. Our fifth panelist is Tyler Lancaster, the principal of Energize Ventures, leading global alternative investments focused on accelerating digital transformation in energy and sustainable industry, with $700 million of assets under management, and they already funded 17 companies to date. Our sixth panelist is Clea Kolster, the Director of Science at Lower Carbon Capital. She leads their technical research, development, diligence, and scientific strategy efforts. She focused on her career on solving the climate emergency through innovation in technology, business models, and policy. Again, a huge thank you to all our panelists, and I can't wait to get some discussion going on today's topics. But first, let me review the agenda for you today, as well as some background on the topics we will be exploring and how you, the audience, will be engaging in today's conversation. After the quick intro by yours truly, we go into 80 minutes of in-depth discussion with audience engagements focused on two high-level starter questions. And we will finish with 30 minutes of open Q&A with questions from you. So please have your cell phone ready to scan QR codes or ready to open a survey link we will share in the chat so that you can join us with a polling tool we will be using to gather your feedback. Now, to briefly frame today's discussion about charging, safety, and grid, I'd like to show a few topics we will likely discuss today, depending on our panelists, and you, our audience. Fast charging, wireless charging, battery swapping, charging infrastructure, electrode structure and cell design, V2G and V2X and other smart grid applications. As now, and as a last step before kicking off today's what I expect very energetic discussion, a final reminder for how the forum will go. We will be focusing our discussion on charging, safety, and grid around two key guiding questions. The first discussion will be focused on the most impactful innovation in charging, safety, or grid that can be realized in the next 5 years, The second discussion will be focused on the most challenging innovation that will disrupt the market in 10 years. Our hope is to have diverse opinions, maybe, I hope, even contrarian views, and aim to uncover what cutting-edge technology trends, business model, and innovation that the energy industry should really be paying attention to. The answer from our panelists should fuel, pun intended, the initial discussion. We will then shift gear and have an opportunity for you, the audience, to get involved. The first way to do this will be with your votes on the answers provided by our panelists. Be sure to have a phone or browser ready to vote. Let's get started. Dear panelists, please see the link in the chat at the right-hand side of your screen and click through to submit your answer to what you think is the most meaningful innovation to be realized in the next 5 years in charging, safety, or grid space. So let's see if we have quick answers coming in. This will be very fast indeed. So the first one is about a device, whether it's a car, phone, or robot, that can be charged so quickly that we no longer worry about charging. Maybe we don't even call it charging by that point. Technology to streamline, permitting an interconnection of EV charging infrastructure on the distribution grid. I have a guess of who wrote this one. Extreme fast charging, XFC. Okay, this one I know who it is. Charging your electric car fully in 5 minutes. Increase V2G, enabled by control systems, battery state estimation, and drop-in power. Electronics cost, batteries will get faster. BMS integration, and V2G becomes a reality. Very nice. Thank you, all panelists. This is time for you to join back. Very good. We have everyone. So who wants to start by this topic of charging a device quicker? I think, Doron, you should go.
Well, the chemistry of the battery is actually the bottleneck of charging. Because we all use, at least in lithium ion, we use graphite in the anode of the battery. And graphite is limited in terms of its resistance, its ability to diffuse the ions, the lithium ions fast. So lowering the resistance of the entire cell, but mostly on the anode side, because when you charge, all the ions need to be pushed very quickly into the anode, which is the negative element of the battery. With graphite, there is a limitation of actually doing this fast. And, we all remember what happened, for example, to Note 7 a few years back, where it was, really a safety concern to start using high power charging for small devices. So today there are alternative technologies that mostly replace the graphite as the active material in the battery. And we have shown it a few years back with the germanium. This was our first generation where we actually charged the phone in 30 seconds. So this is definitely feasible. By the way, when we put the clip online of charging the phone in 30 seconds, we had I think it was 3.2 million hits in 24 hours. Just people wanted to see, this wonder of how you actually charge so fast. So this is real and this is happening. The problem with germanium is cost. Germanium is an element that is not rare, but it's about $2,000 a kilo because it's not easy to extract. It's mostly a byproduct of some coal processing. So germanium is really mostly as a technology stepping stone and the ability to demonstrate the capabilities of fast charging. But silicon, which is a very close cousin of germanium. I mean, if you look at the periodic table, right under carbon, you have silicon, germanium, tin. All those are known to have high diffusion of the ions, low resistance. The problem is that they swell. There is some expansion in volume as you charge because this is like a balloon. You get all the ions in and it inflates. And when you discharge, it deflates. And this motion actually creates some cracks and eventually kills the battery. So, the challenge for everybody and for us as well is to have some kind of protection or coating or some matrix that would hold the silicon in place as you fast charge the battery. And we are already demonstrating similar performance to the germanium with silicon. Now it's a matter of increasing the cycle life, because at least we are targeting the electric vehicle world and not any device. But in some devices, 100, 200, 300 cycles might be enough. But for a vehicle, you need 1,000 to 2,000 cycles of full charge, discharge of the battery. And this is the challenge. But it's definitely happening. It's available in the labs. And, typically when there's such a huge problem that is being solved in the lab, it takes several years, and we'll see it in devices and in mass production. So this is definitely on the path of happening very soon.
Very nice. And maybe a clarification question is, do you see that as realized in 5 years in terms of at scale, or just in terms of proving this works and then can go at scale?
No, we are already scaling. So we are producing thousands of samples to our joint venture in China. We're already shipping samples, but they don't have the full 2,000 cycles yet. We will reach that probably only end of 2022. So from that point to mass production, typically 2 years. So I think I'd say realistic mass production is 2025, which is in line with the 5 years horizon of mass production of fast charging.
Very nice.
5 minutes.
Thank you, Doron. And I want to hear from Claire, and she probably has a view on strategy.
Yes, so our strategy is somewhat different. So it was interesting. The comment on silicon, of course, is the degradation issue. So it's not just about volume expansion and contraction. That volume and extraction exposes the electrolyte, and so you worry about stability. So the Nyobolt strategy is to move up slightly higher in voltage, which then means that the lithium plating issue becomes a non-issue. You move into a stability window of the electrolyte where there's very little electrolyte degradation on the anode. And then you also can access materials with much, much higher mobility than silicon. So silicon's great. I mean, I worked on silicon for many, many years, as most people know, and I'm a great believer in it. But some of these niobium oxides have orders of magnitude higher mobility. And so then you can really get very, very rapid charging. They're also much more stable at high temperatures, so that you then not worry about going up to 60 degrees. This electrolyte stability window means that you open up and you can get different electrolytes. You're not sticking with the same electrolytes that you might have for a graphitic anode. And so the strategy of the Nyobolt company is to really get stability. So you have devices that can last for thousands and thousands of cycles. And yes, the energy density, you take a penalty on the gravimetric, but not on the volumetric. And if you just change the paradigm to almost instantaneous charging, then you can tolerate slightly smaller batteries, and ultimately the batteries become more sustainable. Because I would argue that bigger batteries is also a problem that we need to overcome. And so if you can charge quickly, you can downsize the battery that you might need. And if you're using a robot, maybe your robot has to go back twice, may go back twice as often, but if it charges a factor of 10 faster, you're better overall. So that ultimately is our strategy.
Yeah, I think there is something really interesting when we are going to talk about applications, which is if it's really fast charging, maybe you don't need a very big battery. So
exactly.
Yeah. I want to double click on what you said about stability, especially for the audience. How does it seems intuitive stability translate into safety? Can you double click a little bit on how stability really helps with safety?
Well, there are two issues. One is there's the stability of the different components, and the stability of the anode and the cathode are very important. And that then translates into lifetime. But then there are also stabilities of the electrolyte, which then can result in gassing problems that could result in safety issues. But I mean, in our strategy is to, in terms of the lithium plating, which is the graphitic issue, and the silicon issue, our strategy is a slightly different one, and that would be to operate at slightly higher voltages along the lines of an LTO cell. So I don't know if that's answering your question. But
it does. And it's more granular than just assuming that stability is just safety.
I would like totally. I mean, stability really is, in the first instance, it's lifetime and then safety. And safety is often a number of coupled phenomena. And
during session 1, we talked actually about lifetime and the importance that you have safety that will continue for a long, long time. Otherwise, you're just not helping the problem. I would like to hear from Ping Liu. What do you think about what's just been discussed? And maybe you have some different opinions.
No, actually, I have the same opinion as Claire. Since we take a very similar approach with time fast. The real difference is we use a different element, but the basic philosophy is the same. That we elevate the end of the potential and try to avoid lithium plating. I just want to echo a critical point that Claire made, is that fast charging has to be taken in a context of long life. And those two things very often are closely linked. And since the topic for the forum is about vehicle grid interface and charging infrastructure, so in the long run, from the point of sustainability, if the world is flooded with vehicle, to have them sitting around for 93 to 96% of the time doing nothing doesn't really make any sense. The elements we're not picking up more elements every day. At least it's not a great idea to pick up elements every day. So fortunately, just like what Claire explained, in many of the compounds, the same scientific reason that gave us fast charging, if we have fast diffusivity, small structure change, also give us very long cycle life. So the downside, of course, there are very few systems that can do this. So I think Claire and I are working on two of those.
Very nice, very nice. Now I would like to move to our investors. So this session is special. We have quite a few of them. So who wants to maybe touch on the application side of fast charging? When do you think it's needed and when do you think it's not needed?
Yeah, I'm happy to come in here. And maybe I just want to follow up on some of the earlier comments in that I highlighted BMS integration as being a critical part. Obviously, the materials are extremely important in getting fast charging to be safer and more feasible. But in thinking about the next 5 years and thinking about the fact that fast charging is also important and resilience of the battery is also important in being able to have those cycle times, in thinking about a battery integrated to the grid and both charging the vehicle battery, but also having it potentially provide behind the meter storage. I think that BMS integration is probably going to be a very critical part, at least in this near term, where you could essentially increase the lifetime and safety parameters of a battery without having initially to change the materials. And in terms of the timeline, for now, charging most vehicle users, electric vehicle users, have charging in their homes. Fast charging is going to be critical in order to have a large scale adoption of EVs, and so this is definitely what we need on the near term roadmap. So working on novel materials that make that possible is critical, but there are also things that we can do in the near term that are maybe more quickly applicable.
I like the concept of increased utility, and indeed, then you need a better BMS to be able to address more features. Cindy, I am very sure you have something to say about this topic.
Yeah, and actually, so I have what I had written is actually increased V2G and vehicle to grid. So I'm in the same camp as Clea regarding EV ubiquity and leveraging it and increasing that utilization significantly. And for that, I think the battery itself has to have resilience, safety, and life cycles. And I have a bit of a contrarian view to fast charging. As of today, most of the charging happens at the home and happens potentially at the office as a provided amenity, which could be free. or discounted at home. It's typically at night, so at lower rates. These fast chargers that are out there today actually have significantly very low utilization rates at the public charging station. So they're about 5 to 10%. They're trying to charge a premium for the fast charging, and the voltage, that increased voltage, let's call it 200 to 600 voltage today, and maybe it goes up even higher for the batteries, really does impact the safety and the resilience of those batteries. So I actually think that there is a wrong rhetoric out there whereby the OEMs have now sold this idea whereby consumers should buy electric vehicles because it's going to be comparable to charging at a fueling station for 5 minutes. So don't worry, fast charging is out there and you can get an EV and you won't be stranded. For a couple facts around that is, average time at a fueling station is actually 15 minutes, not 5, which you could imagine 15 minutes is a significant difference, and you don't need 5-minute fast charging. And then the second case is the vehicles today are increasing in terms of the mileage. And so people are buying EVs. Now they're getting more comfortable because the mileage is going from 100 to 200 and 250, and they're becoming bigger, and the batteries are becoming bigger, whereby actually the fast charging is a smaller corner case because people are taking long road trips on average 4 times a year in the US. So I have a little bit of a contrarian view around fast charging being ubiquitous and necessary a lot. I think it's important to think about the utilization of fast charging, the impact of fast charging for battery resilience, and to ensure that to EV adoption, to kind of maybe change that story about that rhetoric that you really need fast charging all the time, because it's not good for the batteries and it's not good for battery resilience.
I really like your additional view, and I would like to ask Tyler. I know we talked about this before, Tyler, where you have a really good analogy. Most people think about EVs compared to gas cars, but you had a different analogy. Tyler, would you like to elaborate?
Yeah, absolutely. I'm happy to. I agree with Cindy in this case. And this comes through our experience actually operating a network of over 2,000 public EV charging stations, one of our portfolio companies. And I think the reality is the way that EV drivers have behaved, and this is shown in the data, is that they charge their vehicles more like this guy than a gasoline vehicle. They charge it at night, they charge it at work, and then in emergency situations, they might go for a quick fast charge if it's available. The reality of the fast charging business model today is, and this is what Cindy mentioned before, it is not a viable business model. You can't make money. You can't make money in fast charging. Now that can of course change with higher utilization rates, the ability to charge higher electricity rates on $1 per kWh basis for those business models, which I think is being explored. And then really optimizing the cost side of the equation by integrating battery into those installations. And then, of course, technology advancement, which folks have talked about. I think that, maybe 10 years from now, my view might be very different. But the sheer reality is on a pure kWh delivered basis, almost all of the electricity going to electric vehicles today is at home or office. And fleets are a completely different topic. And I think actually a fantastic use case for fast charging where willingness to pay is extremely high. And the business case is very well defined. And I think you're seeing that with some of the moves that, fleet sharing companies and other operators of fleets are, establishing partnerships in the fast charging space. But the reality is, in terms of boots on the ground, businesses that are actually operating EV charging networks, happy to integrate fast charging when it makes sense, but for the most part, it's a niche application right now.
Thank you, Tyler. I think today we are blessed to have someone from Cambridge, UK, where they are taking the lead in this space. Claire, would you like to add something?
Well, I just wanted to push back a little bit on the sort of the models on fast charging, and I think your point on fleets is a really good one. But if you're looking at it from a UK perspective, where and an EU perspective, where only electric vehicles will be sold from 2030, you have a massive population who don't have driveways and don't have garages. And so the US model of a car sitting overnight is not one for the rest of humanity. And so I'm not going to sit here and say that the Nile-bought batteries are going to save the planet, but I think we have to think more flexibly about charging. And there will be people who will have to go and rely on charging points and very quick access, because there's going to be no other way. And so I'd like to think that a business model will develop that will enable a larger fraction of humanity to drive electric vehicles. And I take your point totally, Cindy, on stability, on fast charging, and that's why we're trying to develop. And I'm not saying we're the solution, but that's why it's very important to build more resilient and robust batteries that may be cheaper. They may not have the higher energy density, but will actually survive the fast charging requirements, because not everybody has a garage and a charging point. And so we do need to take that on board in our view of the world.
Thank you, Claire. Ping Leo, I think you wanted to add something.
Yeah, I just want to say that some of these sort of apparent disagreement is mainly probably our understanding of the definition of the timeline. Like, what does the 5-year mean? So then in the near term, obviously, the fundamental logic behind right now, a lot of the concerns expressed about whether fast charging is needed or even is a thing, is because my personal view is that the lithium-ion battery put in a car today was not developed to serve this purpose. The primary driver is to lower the cost, give you enough range, so that somebody will go buy it. Having the fast charging or last forever or to serve the grid was not part of the design metric. And this way of thinking will not continue. It cannot continue, just like what Claire was alluding to. If we really believe in EV future, this single-minded design philosophy driven by the automotive OEMs will not work. They have to change. So I don't think that there is a fundamental disagreement. It's mainly, even Tyler alluded to, perhaps in 10 years there will be new battery chemistry that will change how we think about these things. So I think it's mainly a matter of at what time scale we're looking at this.
I really like what you said, and it adds to the points earlier about increased utility, increased features. I also like the point made by Cindy about these 5 minutes versus 15 minutes, where we assume it's fast to charge to fill a car, but actually it takes longer than just 5 minutes. And maybe on the psychology, Doron, do you want to maybe comment about your experience on these 5 minutes?
Yeah, so over the last, I think, 100 years, people have been charging, have been fueling their cars in 5 minutes, right? I mean, you go into a fuel station, 5 minutes, you buy a cup of coffee, have a little break, and off you go on the road for another 100, 200, 300 miles, doesn't matter, what size of tank you have. This experience is what's driving the adoption. If we can somehow replicate the fact that, in 5 minutes, you're off again on your road, and you don't need to worry about, getting stuck on the highway or sitting hours in a charging station. So the experience of the driver should be exactly like fueling, only without the fumes, obviously. So what we are thinking is that not every time you need to charge in 5 minutes. And by the way, we won't start the first implementation in 5 minutes, not because of the chemistry of the battery, but because what we know is going to be available in terms of the charging stations. Because we need 350 kilowatt, maybe 500 kilowatt. For a Tesla, let's say Model S, you need a megawatt to charge in minutes the car. So that won't be available, for another decade or so. So definitely there's going to be a gradual increase in the miles per minute that you can actually get at the charging station. Also, when we talk about the economy and the whole driving force for fast charging, you need to think about the forecourts, all the stations that are already out there with the massive retail business that they already have. they cannot afford, let's say, for example, BP, British Petroleum, right? They invested in Stordot. Why? They have 18,500 stations, gas stations, that in a decade will become obsolete. They have to repurpose everything for fast charging, because if the car sits there, let's say in the center of London, it sits for an hour, then the whole model breaks, right? The retail shop cannot make money, and the real estate model doesn't hold. So fast charging has to happen, and I totally agree with Claire. It's people don't have garages everywhere. Especially think about China, right? They have high rises. You have 1,000 people that need to charge, whether it's the scooter or the vehicle. They don't do it in the garage. They don't do it even in the parking. They do it in stations. So battery swapping, like NIO is doing, is one solution, and it seems to work to some extent in where you can actually invest in the infrastructure. We tried it in Israel, by the way, like 10 years ago with Better Place. Didn't work because the investment was very massive, but it seems like NIO has a better model. But for the most part, people just need to know the psychology of the 5 minutes, that they don't need to do it every time. They just know that when they go on a trip, even if it's 4 times a year, this is the reason they don't buy the vehicle. I'll tell you a story about my boss, my previous boss, Dov Moran. He's the inventor of the disc on key flash drive. He had a Better Place car. And when he heard that I'm doing these batteries, he said, "Oh, you can take my car and play with it." I said, "Why? Aren't you driving it?" He said, "Listen, I'm driving all day, going between meetings, and then at 5 in the afternoon, I get home. I get a call from my son. He's at soccer. He tells me, 'Come pick me up.' I tell him, no, now I'm charging. Cannot pick you up." Because just for this reason, he's not touching the vehicle. So it's the psychology of being able to get in 5 minutes the range that you need, even though you don't do it every time. The battery needs to be able to do that.
Although you could wonder if it was a convenient reason in this case.
Yeah.
Clea, I feel like we are building a lot on what you had said. Would you like to comment more?
Yeah, I mean, I would just like to follow up on, answering Doron's and follow up on some of Cindy and Claire's comments. So, I mean, Doron, I hear you on the psychology, but I think to Cindy's point, this is really a paradigm shift that we need here, and we need to change the way that people think. I think one important thing to note is that, and Claire, I am actually originally from London, and I'm very familiar with the big city life. And the lack of garages there, but charging a vehicle is not the same as refueling an internal combustion engine. Real estate within the vicinity of any refueling station is inherently lower cost because of the hazard that causes. Whereas charging a vehicle does not have the same level of hazards, hopefully, as a refueling station. So I think one important point to note is that we don't need to be thinking about the location of that charging in the same way as we're thinking about petrol stations. And that leads to the point that Doron is making about the oil and gas companies. And I think that's kind of the sunk cost fallacy, where they have this infrastructure, sure, and they're going to lose money on it, but is that that trade-off will be at the benefit of future investment. At least that's what in my opinion. And so we need to change some of that thinking. Maybe we don't have a petrol station the way that we do today to refuel our cars. And I'd love to hear the panel's view on wireless charging. My understanding is that is very far from today, but maybe there's something about that can unlock some of the convenience around charging in different locations and removing this thinking around the centralized fuel station. At the end of the day, if you have a car, whether you're in a big city or in an American suburb, you need to charge. You need to park your car somewhere. So thinking about that setup, I think is really important.
Thank you, Clea. I think we will park the wireless charging for the next session. I'm guessing it's more on the 10 years than the 5 years. But I think we can maybe ask Cindy, because you mentioned gas and oil companies, and I think Total is a company that's now transforming itself and embracing new energies and rebranding itself. So maybe, Cindy, you have more to say.
Yeah, no, and I appreciate the comment. I think it is a challenge that these oil and gas companies, including TotalEnergies, has, whereby we have 17,000 fueling stations around the world. And what is the future of these fueling stations? I completely appreciate and understand the opportunity costs, and transforming them to be EV charging stations aren't necessarily the right thing. There are other opportunities potentially. And I wanted to share something because we are very big in Africa. We're the largest fueling station provider in Africa, whereby I think Africa could be one of the first truly mass market shifts to electric mobility, which is kind of funny. It's the leapfrog effect, I feel like, that the US and the European infrastructure may not have, whereby they have these motorcycle taxis. And these motorcycle taxis are fundamental to African mobility. 2% of Africans actually own a motor vehicle, and they spend about $14 billion a year on the bike, of that 8 billion being fuel. And that rhetoric needs to change because for TotalEnergies, we do believe the future is not and it could be electric versus oil and gas. And so this high fuel spending, coupled with a high geographic density, coupled with a lot of high utilization, so the bikes are swapped every 3 to 4 years since they're driven about 60,000 kilometers a year. We invested in a company that actually is going and saying, we're going to electrify and provide swapping stations, financed e-bikes, and these swappable batteries, so you as an individual driver can actually make more money in your pocket each day. So it's an example of maybe perhaps where we can see more ubiquity of electrification when the economics make sense for the consumer and it makes sense from an emissions perspective. So we're exploring things like that from an investment perspective.
Thank you, Cindy. And I really think you're right about Africa being a place where you can actually nearly start from scratch for a very smart grid. I feel like all of you are very itching to go into a discussion about future. So let's shift our focus to the second question of today's session. Panelists, please see the chat on the right-hand side of your screen. Again, the link to answer what you think the most challenging but disruptive innovation will be in this market in 10 years. And we can start looking at the answers that will come from our panelists. Solid state batteries with energy density of 450, APIs for electric vehicle software apps. Interesting. I like the APIs. I'm a software engineer by background, so this is really interesting when we start thinking about APIs and integration. Ubiquitous excess renewable energy powering low-cost green hydrogen. That's an interesting one for 10 years. A battery that cycles forever and charges in minutes. Okay, this sounds good for 10 years. A better fuel cell catalyst that makes HEV fuel cells a reality. Whether one is found is another matter, so, okay. And cobalt-free lithium cathode and baseload microgrids for charging. So I think we will also ask about microgrids. So I think we have the answers from all the panelists. I'm going to be asking about APIs first, because I think it also touches about business model, integration, and applications, and that will probably then drive to all the other points from the panelists. May I take a guess that, Tyler, you were behind the API question?
Sure thing. Yeah, I'm happy to talk a little bit about this. Obviously, our as a software investor focused on these industries, perhaps a little bit biased, but the kind of extending the cell phone metaphor in how EVs are different than combustion vehicles. So first of all, EVs are inherently connected and collecting data and beaming that data through telecom networks. And what we're seeing emerge now is an entire suite of transactions and software applications that are taking advantage of that capability. And so if you think about like the daily life of an EV compared to a combustion vehicle, I don't know, for folks who are on the panel, I personally fuel up maybe once every 3 weeks or so. And so I consummate maybe 20 to 30 financial transactions with my vehicle per year. When we think about electric vehicles, that EV might be charging, plugging in at home, plugging in at work, plugging in at a public charging station, and consummating financial transactions on the order of 20 to 30 or even more per day, with a variety of parties that are participating in those transactions as well. And to me, that screams we need a common API platform. In the same way that after the iPhone and smartphone was released, a company like Twilio emerged to sort of simplify all those interactions between that iPhone and all the telecom providers and networks that were being leveraged in order to send messages and data across those smartphones. So there's a few firms working on this, but it's sort of that non-obvious picks and shovel play that can enable a whole host of business models, applications, and frankly, the infrastructure itself should one emerge. So and it's going to take a while to develop. API companies are not sort of short-lived, quick development stories. Twilio was launched 1 year after the iPhone back in 2008. First iPhone, I believe, came out in 2007. It took 10 years for them to become a public company, which was, I think, in 2016 or 2017. And they are now a $70 billion company that many people haven't heard of. So for all those developers out there, we're looking for that next API platform to emerge in this space.
Very nice call to entrepreneurs. I think Twilio is a good analogy because before Twilio, every app companies and websites had to reinvent the wheel and do it again and again. And so there's an opportunity here clearly to have the infrastructure, the APIs, to be able to enable companies to innovate on what they can be innovative on. I would like to hear one more investor talking about this topic. Clea, would you like to comment?
Sure. Yeah, I mean, I hear Tyler's point for sure. I think that also goes back to maybe my comment on BMS and the multiple utilities for batteries. We really need to be, rethinking. One, the grid is going to need to, at least in the US, presumably triple or quadruple in the next few decades to be able to serve the level of electrification that's needed for decarbonization and the path that we're on. So that means that however much demand response and distributed energy resources we can have, we should leverage. And that inherently also means that we need very good management systems for our batteries, both for the safety aspect of things, but also in terms of being able to interface with the grid, with electricity markets, and have all of that work smoothly. So, if anybody has a genius solution to that, I'll call out a company that we work with called Enode that are based in Sweden. They're based in Norway, but they're a bit of a remote company. But that essentially would create an API for utilities to have visibility on EVs being charged in homes. So kind of like your Nest for EVs, and so you are able to have flexible load and really reduce that weight on the grid in terms of increased electrification.
Very nice. I nearly feel like there's opportunities for both increased efficiency and effectiveness and enabling more innovations. Maybe Cindy, the last point of view from an investor before we move to the rest of the panel?
Yeah, I actually think APIs for EV storage hopefully is not a 10-year pathway. It's something more on the 5-year side. There are companies, as Claire mentioned, her portfolio company, that are already tackling bits of that. We have a company, AutoGrid, that is also becoming the platform and integrating these devices on behalf of the grid. And clearly, as EVs become, hopefully, as we all believe, that become more ubiquitous and more mass market from an adoption perspective, a cost perspective, that there is the ability to leverage those, as I called out before, V2G is something that I have believed in for 15 years, and hoping that if EVs actually do become quite prolific, we can leverage that as something that's not necessarily utilized for 97% of the time, like vehicles are today, we can also utilize them for resiliency and demand response for the grid without building more infrastructure and assets. So I actually hope that the APIs on EV software is broader than that, and actually is something in 5 years or less.
Thank you. It sounds like all our investors are ready to open the checkbook for this. So this is really good for the entrepreneurs listening in the audience. I would like to hear from Claire. Oh, you're on mute. Yeah.
Sorry. I just wanted to make a very different point. So I agree with all that's said, and I sincerely hope that the APIs are faster. But if you look at the size of the grid, there's somebody who's not muted. The size of the grid to meet the 2050 goals within Europe are going to be a factor of 2 if we're not smart. Sorry, a factor of 3 if we're not smart, a factor of 2 if we're smart. And this is not only going to require this massive integration, there's going to be tremendous security aspects. And that's not security in terms of sort of simple credit cards, it's about whole of the countries going down. So I think this is a tremendous and massive opportunity for people, but it's also going to need retraining. So as the academic, there's going to be a lot more mathematicians who are going to have to be involved, and computer scientists actually get that grid coordination done. So I think it's a really important area. So I hope that progress is made in 5 years too, because it's going to need it if we're not going to have to triple the size of the grid.
I really like your point about mathematics here, and I nearly feel like we have a lot of local maxima, but maybe a microgrid would be a better maxima, for example, in terms of design. Anyone wants to talk about microgrid and how they could actually be really helpful, or actually maybe they are just something that feels intuitively good but wouldn't be?
I'm happy to provide a brief comment, just because I'm the one who put the microgrid comment, and I think that just feeds into the previous question around, or the previous topic around fast charging, whether that's 5 years or 10 years. Regardless, that requires a huge pump up from the grid, a huge drawing on energy, and I think that in thinking about realistically, at least in the places, at least in perhaps North America and Europe, where our grids are pretty extensive, microgrids can be very helpful in reducing that additional pull, and I think thinking about what kinds of miniaturized technologies, baseload energy, potentially nuclear microreactors, but also other things, of course, like solar and battery integration, or potentially hydrogen fuel cells. Those are the kinds of things that we can think about in terms of actually being able to develop widespread fast charging stations, and then probably most importantly in places where grid access is more scarce. Microgrids are likely to be a very critical portion of having charging stations, if that's the way that we go.
Thank you, Claire. I would like to hear from Doron, both on the microgrid, whether it's something you think a lot about or not, and then moving into maybe the chemistry, like solid state and maybe cobalt-free cathodes. Can you start with the microgrid and then expand on the chemistry side? You're on mute, I'm afraid.
I think, sorry, we've discussed several times in this panel the need to rethink the models, and I think the grid really need an overall rethinking, because the grid was not designed for these peaks of charging, whether it's even slow charging, but mostly fast charging. When people go to work or at 8 a.m. or they come back in the afternoon, the grid cannot support what is going to happen in charging. Like if you think about Oslo, for example, where you have 30% adoption already, there's a new charging anxiety. People are worried, that as they get closer to the charging station, there's going to be a huge line of vehicles want to charge, or they need to sit there for 2 hours before they get home. That's a charging anxiety. So the grid needs to be able to support high power 350, 500 kilowatt stations. And the only way to do that is with some buffering. Now, buffering can happen with second life batteries. It can happen with microgrids. It can happen with vehicle-to-grid connections. But I think all these solutions will have to be in place, and various strategies will have to be implemented around the globe in order to start supporting the huge adoption of electric vehicle that is coming over the next 5 to 10 years. So I think definitely microgrids will play part of it, but there's going to be a host of solutions for leveling up the requirements from the entire grid. Now, regarding solid-state batteries, and I know there are some companies out there that are claiming that it's really around the corner, maybe next year, we'll start seeing vehicles with solid-state batteries driving 1,000 miles, and they have many cycles. I don't believe that. I mean, we've been working also on solid-state batteries for a while. There are many, many challenges with solid-state. I'll just name a few of those, and mostly the interface of solid-to-solid movement of ions, where you need to move the ions not through a liquid like in a normal battery with the electrolyte, but you need to move it through some solid electrolyte. And you have actually 4 of these interfaces in one solid-state battery, because you need it from the anolyte to the active material of the anode, then to the separator, which is solid, and then back to the catholyte and to the active material, let's say NMC, or nickel-rich or manganese-rich, whatever cathode you're going to have. Each of those have not been solved. Especially it has not been solved for fast charging. So yes, you have some lab prototypes of 4 layers, maybe 10 layers, of 30 by 30 millimeters that can demonstrate very slow charging at room temperature of some prototype. But the gap from that prototype to a vehicle that can actually deliver a user experience that is reasonable and at a reasonable cost, because these factories need to be built. That this is not the existing capital equipment that we already have out there. So building a factory is 3 years, even if you're Tesla, it's 2 to 3 years. And then, ramping it up and getting to the right yield and to the right cost of, let's say, 80, 70, 60. These are the numbers, dollars per kilowatt hour. Who knows? So I think this is for the next 10 years. This is something that should happen. It probably will happen, but it will happen much, much slower than what people think.
And first, I'll make a comment as an investor, which is around the corner in our hard tech space. It's probably 5 to 10 years anyway. It's not like a mobile app. But also, I think we should be talking about the impact on the planet. How can solid state and this new technology really help in terms of sustainability?
Well, first of all, you will need fewer of these battery cells, because the energy density jumps, let's say, from 300 to maybe 500 watt-hour per kilogram. Then you need less of these batteries. Plus, if they can cycle, like we mentioned many, many times, thousands of times, then you don't need to, dispose them so quickly, and they can live for, let's say, 10, 15 years instead of 3 to 5 years today. So that's one big help. The other big help is the elimination of cobalt, obviously. That is happening, by the way, regardless of solid state. But in solid state, it has to happen because we need to replace the cathode anyhow. An NMC cathode cannot really sustain more than 300 watt-hour per kilogram. So we have to go to eliminate the cobalt, have more manganese or nickel in the battery, in the cathode of the battery, but this is still in development. So that helps the planet in the sense that less batteries that you need to dispose, less materials that you need to extract from Earth, but most importantly, less materials such as cobalt that have many issues like child labor and really geopolitical problems that can actually create wars. And this is the new oil, right? So there's going to be a war over the batteries. So we need to make sure that at least, in some disadvantaged areas, we don't keep jeopardizing the stability there.
Yeah, on a serious note, I think there will be wars around this for sure. I want to ask Ping Liu and then Claire. I think, Claire, you were the first one to comment about the size of the battery, and we shouldn't look at making them the same size, but making them smaller. But Ping Liu, could you share your thoughts about what Doron just explained?
I just want to comment on the topic of solid-state battery. It's for full disclosure, I work on it myself. It's a fun on a mostly frustrating topic to work on. But from a consumer perspective, first of all, let's be clear: a consumer who buys a car has no clue whether the battery inside is solid or liquid. They don't really care. They have a spec sheet that I want A, B, C, D, E, and as long as we give it to them, they're happy. So scientifically, solid state brings a lot of opportunities, including actually making battery run faster counterintuitively, because the interfacial process on a good day can actually happen faster than in a liquid electrolyte cell. So it can work theoretically. To make it practically work is very, very challenging. Now, the new science is happening every day. So this is an exciting area, I would say. But will it materialize, become a viable technology? Particularly, even if all the science has been addressed, will they become viable on a mobile platform like in a car? Because most of these solid electrolytes are inorganic materials. So there are additional challenges in that regard. So I would say, if you ask me like what I think is the future, from a commercial viability perspective, I actually don't know. I think we are making new discoveries every day, and most likely, a commercially viable product will emerge. But I don't have the magical 8-ball to tell you which one or when.
I love your answer, especially coming from an inventor like you. This is really commendable. I would like to hear from you, Claire, both on the size of the battery. I think you alluded to it, but we didn't double click on it. And then back to the chemistry topic.
Well, just as quickly on the solid state batteries, I think that when people quote these higher energy densities, they're sometimes slightly misleading, and they take on board the fact that you either have to get silicon in there or lithium. Most of them are based on lithium. And if you have lithium, then you've got to deal with the issue of dendrites. And so you're back again against stabilizing lithium metal. And the idea that the ceramic is this impermeable thing that you can't get lithium through is a misnomer. I mean, lithium is a bit like ivy. It finds its way through the little cracks and it opens things up. And then you put a solid state battery in a car and it's jiggling around. And you think about what happened to the Dreamliner batteries when the vibration aspects and testing weren't due. So I think it's a challenge. I mean, I work on solid state batteries too, full disclosure. And it's from the science perspective, it's extremely interesting. And then if you have lithium, you've got to get the lithium to actually fuse with the ceramic. And so that requires pressure. And so in order to get that to work, you've got to redesign the batteries. So I think it's a really cool area. I think I think that we will get batteries to work. Whether they'll make sense in a car is another matter to me. But so I think it's longer than people think. In terms of the cobalt-free batteries, just quickly, I think we have to do that. It's going to bring in a debate about whether we will actually switch to sodium batteries, where actually finding a cobalt-free battery is easier. But then that will then become part of a debate as to in which markets can we tolerate lower energy density batteries. And so we talked about batteries in some parts of the world where that might be a more appropriate solution. And there you could see the development of a totally cobalt-free based system, and that might even involve sodium. So
thank you, Claire.
10-year market, that's a possibility. And then smaller batteries, I think that's sort of fairly obvious. If you can, dare I say it, charge faster, and so you don't worry about range anxiety, then you can tolerate a smaller battery. And that's very good that's the easiest thing for sustainability, is to reduce the battery pack.
Yeah, this makes sense. Talking of sustainability, some of you answered, of course, batteries that cycles forever. I think that's one where you wouldn't need to recycle even, so that's really good. But some of you mentioned low-cost green hydrogen and hydrogen fuel cells that become a reality. I want to hear from you about this topic, because we've been talking a lot about batteries, but this is not just about batteries. Who wants to go first?
I'm happy to share my thoughts, Nicolas.
Thank you, Cindy.
So it's interesting, as I listen to the conversations about the grid and microgrid that Claire brought up as well, and Doron talking about the grid. Well, the grid used to be the cheapest battery. I don't know if 10 years ago, 15 years ago, we used to talk about, oh, the grid's the cheapest battery. And to Claire's point, the fact that in Europe it's going to have to triple in size, and that's not a cheap infrastructure investment. And so one of the things that I think that could be quite innovative and could be quite disruptive if there is a significant amount of excess renewable energy, like we're seeing in the North Sea with a lot of excess wind capacity. Could you take that and store it in a medium that can be transportable and used later? And as we know, electrons are typically stored in batteries or on the grid, and that's not very it may not be very transportable. And so that's why the concept of green hydrogen could be quite interesting as a potential storage medium, kind of electrons to molecules. And we have pipelines, for example, and natural gas pipelines that TotalEnergies has, and then we could leverage those from a transport and storage perspective. There are its own challenges as well, I admit. But I think, as the cost curve comes down and the modeling comes down for green hydrogen, you can imagine if it gets down to $1 a kilogram, that a lot of use cases could open up, even to transportation, for example, for long haul, for shipping, for planes, whereby it could be another fuel alternative that could be quite interesting for the transportation industry, not just the charging side from a battery perspective.
Thank you, Cindy. Tyler, I know that you have some of your limited partners who really care about carbon zero goals. What's your view on hydrogen?
Yeah, it's an interesting one. I remember almost 7 years ago when I was still a consultant, still a recovering consultant, and one of our clients asked us to look at hydrogen back then, and was there a pathway to $1 per kilogram hydrogen if we threw everything we had from existing nuclear plants at it that were experiencing negative prices in many of the wholesale markets and still are. A lot of RLPs have made some initial forays into hydrogen, and I guess one of the learnings which has surfaced, because I do believe there will be an economy that emerges around hydrogen, because there's simply no other way to address many of the high heat processes, in the industrial world with electricity, or at least not a clear pathway to me yet. Is I think that one of the problems we have right now is that for hydrogen projects, you essentially have to assemble an entire value chain. You need to solve for production. You need to solve for transportation, distribution, oftentimes with existing infrastructure if you can. Otherwise, it's too expensive. And then you need to have firm offtake. So one of the clever ways that an LP has solved this is they're producing hydrogen from the sun and the wind via electrolysis. They're moving hydrogen through existing gas pipelines to an existing gas plant that is designed by GE to burn up to, I believe, 60 or 70% hydrogen without suffering any damage to the metals from those becoming brittle. So I guess my point of view is, like, over the next 5 to 10 years, we'll have to find very creative ways to get this industry off the ground. Fortunately, there is some policy support, hopefully coming down, that will ideally do for electrolyzers what many incentives did for solar and batteries in terms of learning curve dynamics. But I'm of the opinion that hydrogen writ large is still 5 to 10 years away. So maybe it fits well within the timeline of the question from that perspective.
Is.
Yeah.
Great. Thank you, Tyler. I think we should ask the third investor. Clea, what's your view?
Yeah, I mean, I guess both of those comments are great. I'd like to just briefly comment that there is a huge industry today for hydrogen, and it's pretty dirty, as we probably all know. Most of that used for fertilizer production, and of which only a few percentage of that hydrogen demand is actually made via electrolyzers. But there are definitely some edge cases, potentially in aviation, potentially in heavy industry, where there might be a future in which hydrogen could be a critical path for decarbonizing those. I think it's really important to initially focus on decarbonizing the existing demand. But to the extent that people are working on novel electrolyzer materials and configurations that can achieve higher efficiency, but also very importantly, not too dissimilarly from batteries, electrolyzers also require a whole slew of materials that are difficult to access and very expensive, and that make it challenging to scale. I think there's a lot of work to be done there in getting electrolyzers and green hydrogen to achieve the kind of costs and scale that it would need. And to all of the earlier points, for electric mobility to really take off on a very, very universal scale. Similarly, for hydrogen to take off for transportation, you need the infrastructure, and right now there is no infrastructure associated with hydrogen refueling. And I think the challenges around locating hydrogen are a lot greater potentially than electric charging because of the flammability and hazard around that and the requirements for storage. So just putting those comments out there. Again, we're all ultimately wanting to get to a net zero path, and for that you need a lot of different solutions, and there are challenges in the way.
Thank you, Claire. And I'm going to double click on you because I don't think it's obvious to everyone. I think in the audience maybe, but and the panel for sure, but it's not obvious hydrogen is green. And could you double click on the electrolyzer and why this is the way to go?
Yeah, sure. I mean, so currently hydrogen is produced mostly via a process called steam methane reforming, where you essentially reform natural gas, and the result in very simple terms is hydrogen and CO2. There are options for that to be retrofitted with carbon capture and storage. And well, I spent 4 years researching CCS, and while in some cases that might be a viable solution, I think that ultimately we need to, as much as we can, move away from relying on natural gas. I know that that's probably going to be a little bit of a contrarian view, but to the extent that there are a lot of different points in the natural gas supply chain that are challenging for the environment and in terms of their global warming potential, that mean that CCS in and of itself is not the only solution that you can rely on. So to that said, that alongside the fact that in theory we're getting much better at generating electricity from renewables through solar PV and wind, and electricity costs is going down by enormous amounts. Obviously, there's a huge amount of energy shifting that needs to happen, but that has otherwise been the main barrier to electrolysis being deployed at large scale, because electricity costs were never as cheap as they are today. And so in that path towards decarbonization and part electrification, I think electrolyzers with green electricity are a very key component of that.
Thank you. That's really, really nice explanation. And I'm going to ask Claire to comment, and then we will move to the audience polling. So for the audience, get prepared. Claire?
Yeah, just a very quick comment. The electrolyzer and the fuel cell require a catalyst, and the catalysts are platinum based. And so they don't have to be platinum, but they're platinum groups. And so that's very expensive. And that's been the same way for the last, forever, essentially. And so the problem with the whole hydrogen field, it's very difficult to predict. And we talked about solid state batteries and the difficulty of predicting whether they were going to work. The same thing is there for fuel cells and electrolyzers, except they have been studied for a long time. And so it's very difficult to imagine how to design from the lab-based a projection of when these things are ever going to be ready for fit for purpose. At least with the lithium-ion batteries, we have sort of technologies that's sort of good enough, so you can have a roadmap. But it's very difficult for that roadmap for hydrogen. And then the other thing is that there are intrinsic energy penalties associated with the reactions where they're actually quite inefficient. And so again, when we talk about trying to be efficient, that they're not going to be very effective. And so when then you think about an HDV, so I was the one who put hydrogen in the response, how do you think about reducing emissions through the fleets of lorries when we can't actually get a time frame for when a fuel cell will be ready and the batteries are so large? And so I think that's a massive challenge coupled with the fact that energy storage of hydrogen is very inefficient. And if you think about trying to do storage for a boat, you're not going to do hydrogen, you're going to have to do ammonia. And then if you're going to do ammonia, you've got to deal with the ammonia emission. So hydrogen is a complex problem right from the beginning and the chemistry all the way through to the distribution and all the other things we talked about. So that's all I want to say.
Absolutely complex. And I think it fits really well within the 10 years time frame that was part of the question. Okay, time to open up the floor to feedback on this discussion from our audience. So now is the time to get your phone ready, to scan the QR code, or your browser ready, as you will be able to vote on the answer to each discussion point that you thought was the most exciting or interesting. So as you see the QR code come up on the screen, you should also be able to see a link on the chat section on the right-hand side for the audience to go to the polling page. You will be asked first what industry sector you are joining from so that we have a view about the answers afterwards, and followed by a new page. So stay on the same web page where you can vote on the panelist answer to question 1 that you found most interesting. And stay on the page because we will ask later question 2 on the same page. So don't close your tab. Okay, so let's have a look at our audience. So we have startups, entrepreneurs, and investors. Other. Okay, so this is starting. Okay, some from the industry catching up. Very nice. So it looks like the investors were very eager to answer the QR code the fastest, and now the industry is catching up. We have 15 seconds left to answer for the audience. I don't have a lot of academia. I was expecting more from the academia to be joining the audience today, but industry, startups, entrepreneurs, and investors are very well represented. So the voting is closed, and you should be able to, in the same page, be able to answer the next questions. Okay, so let's see. So this is where we need to really increase the size and see who is answering what. So we have fast charging device, streamline permitting, extreme fast charging, V2G, and BMS integration. I can see that it's spreading quite nicely. Fast charging device is taking the lead. BMS integration is overtaking. It looks like the lead is between fast charging, extreme fast charging, and BMS integration. So actually, if you were to combine both fast charging and extreme fast charging, this would be a strong lead. I think that's going to make many of our panelists happy. V2G is taking a comeback, very nice, and that comes from entrepreneurs and investors and others. Extreme fast charging is really taking the lead on the investors. So most of the investors believe in the extreme fast charging. Oh, wow, this is really going fast. 10 seconds left. BMS integration is actually very interesting. It's really widespread across academia, industry, investors, entrepreneurs, and others. Okay, the voting is closed. So I'm going to ask the panelists to comment. If we can go back to the answers of question 1, please. Oh, this was the question 1. Sorry. So let's move to question 2. Okay, very nice. So stay on the same tab and you can go ahead. We have 1 minute to give the answers. Okay, API is taking the lead first. And then low-cost green hydrogen, both from investors. All right. Now it's getting through all the answers, including solid states, low-cost hydrogen, battery charges. Okay, we have good diversity on the low-cost green hydrogens, including from entrepreneurs, investors, and industry. Solid state is really for investors at this point. Okay. Green hydrogen taking the lead. APIs making a comeback with very nice diversity from all across the industries. So I don't get a lot of love for cobalt-free and hydrogen fuel cell. Okay, just as I said, we start to get some love. That's nice. 10 seconds left. And so far, the low-cost green hydrogen is really taking a lead with APIs just behind. So the discussion we had probably influenced the answers. And the voting is closed. So this is really interesting, and it feels like we have a race. So if we could go back to the result of question 1. Thank you. And extreme fast charging. I nearly feel like I should ask, let's go with Doron first, especially when you see the majority of investors wanting extreme fast charging. What's your feeling?
Listen, I'm not surprised at all, because every investor we talk to, by the way, also every OEM of a vehicle, the number one concern is the charging. Now, whether it's fast charging or extreme fast charging, I think it's an evolution thing. Obviously, we are starting with fast charging, and it requires more and more infrastructure. As the infrastructure matures, you would need chemistries that can actually sustain the high power charging for long life and for safety. And this is why extreme fast charging is maybe longer into the 5-year horizon. But definitely, without fast charging, we won't have mass adoption of electric vehicles. It's absolutely critical for the whole global adoption of electrification is to have fast charging. Otherwise, it's inconvenient and people won't adopt it.
Thank you, Doron. I want to give to anyone who wants to jump on the results and maybe answer what was the most surprising. So Doron was not surprised. I want to hear who was most surprised. Or was everyone not surprised?
I would say I was not surprised. It looks like the two areas of impactful innovation are fast charging and essentially, to me, BMS integration and V2G are quite similar in terms of what they are trying to represent, which is utilizing vehicles for more than just the driving piece of it. So I think it wasn't too surprising that those are the key topics that we talked about, as well as the ones that the audience voted for.
Very nice. And Claire, I think you were saying something.
No, I was just about to say, I was just going to first of all joke, so if it's important to invest in us, but I also think that if extreme fast charging is going to be a reality in 5 years, it may also require a change in perspective and user way people use things. And so extreme fast charging being the highest vote doesn't necessarily mean it's the easiest. And I think it will happen, but it will happen in different types of devices and different applications and different modes of using batteries.
I can jump in here to comment just on the obviously most boring and least sexy of the options, which was about permitting EV chargers, which the reason why I had included this in here, we're feeling this pain very viscerally. It's almost impossible to get new EV chargers, whether they're fast, extremely fast, or very slow onto the grid right now, especially the distribution grid. We're evaluating, conducting the interconnection study and assessing the impact on the lower voltage areas that don't have quite as much capacity to push power through, is creating a massive log jam in terms of preventing EV charging infrastructure from actually being deployed. The average right now is anywhere from 3 to 9 months from initial sort of submission of a permit, and then all the way through to utility interconnection analysis and then actually getting into the install process. And so if you're just talking about what is a massive limiting factor in the next 5 years to actually have real impact, figuring out how we fix those problems, which have plagued the solar industry as well in terms of soft costs, I think is actually going to be very important, at least here in the US. I don't know if other markets have perhaps figured it out, and we just can't get our act together.
Thank you, Tyler. And I think if I'm cheeky, the fact there is so few answers on what you believe is going to be the most needed is probably good for you as an investor.
I guess so. No one's looking at it.
Exactly. Ping Leo, you were going to comment on Tyler.
Yeah, Tyler, I think towards the end of your answer, you probably gave the reason away. I wonder whether your view is primarily a US-centric view, like where permitting is really, really painful. How about the global view, like in Europe and other markets?
Well, we know, for example, that Australia has figured out how to get new solar arrays permitted extremely fast, and that has reduced, led to cost reduction on the order of 60 to 70% per watt for solar in Australia. I think that's largely true in other markets that have less red tape and bureaucracy involved in approving infrastructure. So I think you're probably spot on. It might be a U.S. exclusive problem, although I would suspect that in some cases in Europe it's a challenge as well, just based on some of the companies that we've talked to, where the utility studies still take quite a while, irrespective of what type of infrastructure you're talking about.
All right, thank you. I just want to take a minute to also comment on the answer of the fast charging. It's a 5-year time frame. I think for anybody who work on batteries, like Claire and I work on battery chemistry, and for all of you who work in the battery industry, to take a new type of battery to a commercial product, 5 years is nothing. Doron would know this. So there's a desire of having something ready in 5 years. There's a reality how long it's going to take. So I think some of these choices might be also a reflection of the aspiration of the audience. So,
or the hopes, yes.
Yeah, yes. The hopes, yes.
So let's move to the results of question 2. So let's go on the bigger horizon where we can dream bigger. So here I would like to hear who was the most surprised.
I can, I'll comment. Well, I was, I guess, most surprised that that my answers around cobalt-free cathodes and microgrids for charging were the least popular.
Yeah. And what did you find the most inspiring?
I'm gonna flip that question and maybe highlight the fact that solid state and low cost green hydrogen were the most were two of the most popular. I think what some of the rest of the panelists highlighted too is that these are actually very, very challenging. So while it's great that a lot of the people here are working on at least the solid state side of things, to Claire's earlier point, and perhaps slightly contradicting my own, low cost green hydrogen I definitely think is in the horizon, but the materials challenge and system challenge around integrating hydrogen need to be top of mind, and a lot needs to happen for us to get there. So
no, it's in the horizon, but not without challenges.
No.
Very good. And Claire, would you like to comment on the result?
Yeah, I'd like to comment on the cobalt-free cathodes, because I think that comes back to this thing about aspiration rather than reality. And I just personally believe that we have to do cobalt-free, and we're essentially doing cobalt-free in the form of lithium iron phosphate. And I think it is such an essential one. So I feel that actually if we come up with a high energy density cobalt system, it will be completely disruptive. So I just think it's just not very as exciting, and that's why it doesn't hit high, but it's an absolutely essential part for sustainability that we have lithium-ion batteries that have no cobalt in them or little cobalt in them.
I think I'm going to defend
all sodium-ion batteries.
I'm going to defend our audience, because the way we frame the question is, what is the most challenging innovation that will disrupt the market? I have no doubt the audience would all want cobalt-free in the future.
Yeah, well, that's why I suggested if we could actually get an HGV-based fuel cell, that would be very disruptive. So
very disruptive.
Maybe I would just like to comment that 10 years is, and to the point of Ping Liu, he made a very good comment about the timescale effects and how sometimes timing is not necessarily, things may happen in different timescales. And I think 10 years sounds like a long time, but I think in an investor world and especially in creating new technological innovations and building gigafactories for OEMs, for electric vehicles, and building the infrastructure required for low-cost green hydrogen, these are really, really hard problems, and 10 years is actually not that long. So I do think kind of in the context of that, all of these are actually quite challenging innovations in a 10-year timescale. I just think that as investors, we're also very hopeful that the entrepreneur community and the academia community are working very hard to get us there in that timescale.
Yeah. Anyone else wants to comment about the timescale itself?
Yeah, I totally agree. Started 10 years ago when I discussed the 30 seconds clip of the phone charging, very quickly. We are 10 years later, and in these 10 years, we basically managed to take it into a large form factor and, do some experiments of vehicle integration and scaling up some prototypes. But even from here to mass production, we still have few more years. So yeah, 15 years is more like, reasonable time frame to take a new technology from the lab to mass production, let's say in the automotive industry. It's faster in the semiconductor world where, things are much more predictable. My background is in flash memory. Once you have a design of a chip and, the simulation works, you take it to TSMC, UMC, or whatever and they make it for you. But if you have a formulation of a new cell, how to scale it up, the fact that it works here and it doesn't work in China, now go figure why it doesn't work. There's so many components and additives and molecules and mixing and humidity issues and what have you. So there's 15 years is actually more likely to take such a technology into the market.
Yeah, thank you, Doron. I will take one more reaction before we move to the audience Q&A.
So Nicolas, if I may, since we have been sitting here for over an hour, it's time to start some internal war. So I will put you on the spot. So since you wrote the question, so as an investor, I'd like you to provide a definition of 10-year. What do you mean by 10-year? So is it that, in 10 years, you as an investor will get your money back, or 10 years we got a commercial product, or 10 years our commercial product is showing promise to actually address the real issue? Like, what does actually it mean?
I love this question. So let's do a fire response here. Tyler first.
Let's hear yours first, Nicolas.
Okay, so 10 years would be, it returns my fund in 10 years from an investment, which probably means it's probably in the lab or already in prototype phase today. I like Cindy putting me on the spot. This is really nice. So now, Cindy, you're next. I'm sorry, Tyler, but now we go back to Cindy.
Of course, right? I mean, I think about it from the Clean Tech 1.0 timeframe, and the average time for a fund to return if it was successful, was 14 years. And that means that it doesn't necessarily mean they're investing, an investor is investing at the lab scale or at idea scale. They're typically at some sort of prototype and beyond that. So maybe the company's been around for a couple of years when the first investment dollars go in. And if you say from a Nicolas perspective, it's when the funds return, and the average fund returns were 14 years, now we're talking almost about a 20-year company. To get to the fund the exit. And perhaps today you're saying there's more opportunities for IPO and more opportunities for M&A, and people are acquiring earlier, so you could reduce that time scale a little bit in terms of when the exit is and whether that is actually 10 years. But I would say 10 years to return a fund is still ambitious and would be considered, I think, a success.
Well, I think if you ask anyone in my team, they will tell you I'm a little ambitious. Tyler, you're next.
I mean, I can barely get our investors to think about a 6-year investment horizon, relative to a 2 to 4 when they start asking about what's going on with the portfolio. So, perhaps that's in part due to our investment strategy focusing more on asset-light businesses, but 10 years feels like a millennia to me. Yeah.
So back to the question from Ping Liu, what does 10 years mean to you?
So if actually I don't have to create any data point. If we study the history of, say, battery startups, I mean, it would take average, at least in the US, on that order, to produce what I call commercially relevant prototype, right, with enough data, independent data, to substantiate any claim, any potentials. So that would be, I mean, it takes, if my observation is right, 10 years about the time each company has taken.
Okay, I will ask Clea to close on this topic. Sure,
and I was actually just going to point a question back to Ping Liu, but I'm not going to answer with a specific timeline. I would like to know, as an investor, if you do have a new battery chemistry, then what does that actually mean for the timelines to get that to manufacturing scale? And my guess is that today those things are different than they were 5-10 years ago. So I like looking at precedents, but at the same time, I like to believe in bending the curve, and I think that we can do that, and we probably really do need to do that. So, is 10 years enough for a new battery chemistry that is going to be the most critical component of getting fast charging, safe battery safety, and ideally cobalt-free, high energy density battery out there? Well, I'd like to return the question to you all.
Okay, but before that, we should respect the audience. And for the next 20 minutes, we're going to open the floor completely to our audience. And hopefully some of them will come back with the same question. So if you are joining us in the audience, please feel free to post your question in the chat section, and our panelists will be able to respond. And while we wait for the first questions, Ping Liu, if you want to answer the question from Clea, or maybe Claire.
Of course. I think Professor Grey can come to my rescue if I get into myself into trouble. So I think it really, just like your investor talk, it depends. So if you invent a technology that can be quote unquote a drop-in solution, presumably the path will be smoother and faster. If you can utilize existing infrastructure, if you have to build an entirely different manufacturing process, then that would take a very different timeline. The additional element is where you are pursuing your innovation, whether you're surrounded by a robust supply chain infrastructure. If you are in the middle of that, things will happen. You walk across the street, you can get your prototype down, versus you build everything yourself. So it's really a complex question to answer. That's why I only pointed to historical data. So it can be faster, it can be shorter, I would say.
Very nice. So we have many questions flowing us. So I will start with a very good one on energy density. Are these energy density numbers in the application or in a temperature control laboratory in a single cell sample?
So if we talk about the 300 watt-hour per kilogram, this is what we have today with the silicon anode. We're talking about a single cell in a range of temperature -20 to +60 Celsius. And actually, this is the spec that we have received from our OEM partners. So we're actually designing to a spec that is sufficient in 2024 for mass production.
Okay, so I will move to the next question about will hydrogen beat solid state in HGV? Here I'm expecting a diversity of opinions, so whoever wants to jump in first.
Again, if this is for electric vehicles, is this specific for electric vehicles? I don't believe hydrogen has much, competition with solid state. Solid state will definitely take over just because we are already putting the infrastructure for charging and batteries. These are huge investments that would continue with new and newer generations of batteries, post-lithium batteries, but not hydrogen, because that's a totally different infrastructure that may be required, and maybe for trucks, maybe in some niche markets, but not for the mass market.
But HGVs are not a niche market. They're the heavy goods vehicles where you really have problems, and solid state batteries are not necessarily going to be the obvious solution. So I think the jury is out on this one. I'm going to be an academic and sit on the fence, but I don't necessarily see it solid state batteries that are going to be the solution. I think it has to be.
Oh, go ahead.
So it may have to be a redesign of the whole infrastructure of the roads, where you have shorter. If you're going to put a battery, then you're going to not going to do long distance driving of heavy goods vehicles. They will be over shorter distances, and then there'll be charging networks, or there'll be overhead cables. So HGVs needs a complete rethink that will either be a different network or a better catalyst and fuel cells.
If I can add my little investor push in here, I agree with Claire completely, but I'd like to put in a ping for a company that we work with called Remora Carbon that have developed a mobile carbon capture device specifically for heavy duty vehicles, because currently there are not really whether it's batteries or hydrogen fuel cells, neither of those solutions today are really viable for heavy duty 18-wheeler type trucks that are traveling over long distances. So that's one to look out for.
Thank you, Claire. Let's move to the next question from the audience. Are batteries with these types of very fast recharges always safe, and their lifespan changes?
So it's me again on the extreme fast charging. I mean, this is the whole development. Why are we replacing the carbon with silicon? The reason is safety. We do not want to create the metallization or the dendrites that we have mentioned. And part of the development is to make the electrolyte and the whole system of the cell a safe environment. So the very rigorous testing that it's dozens of tests of nail penetration and drop and pressure and temperature that the battery would need to go through. But the whole point is to allow safer batteries.
So far, we have not, the industry writ large, or whether you're talking about the existing chemistries that have been in the field or the new ones that are coming out going forward, I think we clearly have not done a great job of understanding how we plan to actually operate these batteries will impact both degradation and potential safety incidents. So I think there will need to be some form of like supervisory layer and standards that emerge, irrespective of what chemistry you're talking about, that can track and kind of take in data and create feedback loops to ensure that we are operating these batteries as safely as we can, because there's just like too many examples of false starts that have happened in our are creating the type of marketing that a nascent industry really does not need to deal with GM's recent recall and all the grid scale storage fires that have happened. So that would be my only comment on this topic.
Yeah, so I think the next should be an investor, because we talk about false starts and the investments in the past. And Cindy, this is your chance for a contrarian view.
It's funny because in terms of batteries for OEMs, the life cycle needs to be long. Whether it can take fast charging, it always has to be safe. So I think, battery resiliency and the testing that Doron was talking about are going to be critical. And there are so many different technologies today and so many innovations that are in the labs, which is fantastic, trying to replace the silicon anode, whether they're doing on the cathode, there's improvements on the electrolyte. And all of these, I think, are great potential innovations. But I think also from a lab perspective, and also solid state, sorry, I forgot to mention that, Ping Liu. But in addition to all of those technologies, you have to actually be able to manufacture them at scale at a low cost. So from an investor perspective, we see these great innovations that great companies and great entrepreneurs are working on, and then we have to kind of see the pathway and believe the pathway that this can get to the right safety, the right resiliency, the right life cycles, hit all the metrics, but also hit the cost and the scale. And it's a long path, and I think it's hard. And I really commend entrepreneurs that are working on this. We're definitely looking at all these different innovations and areas, and we try to help because we actually own. We're going to build many gigafactories in Europe already as a company. So we believe that partnering with these new technological innovations will be the key. And whether it's a battery manufacturer like ourselves or an OEM manufacturer that's getting into battery cells, that marrying needs to happen of the technology innovation as well as the scale manufacturing.
Could I add a very quick point about safety? I think one of the challenges is we can do all these tests, but we're talking about millions and millions of cells, and you can't individually test every single cell. And so there is something really to be said for redesigning the battery chemistry to make it inherently safer, which is what we're trying to do in Nyobolt to reduce the lithium plating, and without sort of selling the technology. The point I want to make is that if you look at the previous incidents in the past, like the Samsung Galaxy notebook, there were very few devices that actually failed, and you can't test at that level. If you sell 3 million batteries and you maybe you have to test a very high fraction of them to identify the failures. So there really has to be a reinvention of the technology if you want to get rid of some of the safety aspects.
And that touch on what Cindy just mentioned about going at scale, which we haven't touched a lot.
Yeah, exactly.
So Claire, do you have some maybe academia mindset about where do you think the industry should be really looking into to address the fact that you have this safety must, but we need to make it work at scale, and this is a totally new challenge?
Well, I mean, I think that's why. I mean, again, I work on battery degradation, and I think we need to be smarter in picking up degradation processes, safety processes, so that we can see them on the fly. Because it's not just safety in that first few cycles; it's the safety in the lifetime. So, and then we need to build that intrinsically into the battery design. So, our approach is to use a slightly higher voltage anode, but that's not the only way. Whether it's smarter separators, whether it's in onboard detection, better machine learning of signatures that would predict some sort of failure down the road. That all of this has to happen, and these are, at the moment, these are lab-based projects, and they need to be moved through into the marketplace.
I think these are good pointers for the entrepreneurs in the audience. I'll take a few more questions from the audience. So one is, what will happen if all the cars are EV and all connected to the grid, so the V2G, getting involved in the energy storage systems, being charged, discharged several times a day, which actually makes sense in a way? Any concerns on battery cyclability and battery states of health?
Because I would be happy to comment on this.
Yes, please.
like I said earlier, that it really depends on the design philosophy of the battery by the OEM. So if you design a battery that will meet your warranty requirement in terms of cycle life, and while minimizing initial investment, this question is totally legit. If you heavily use, that's why a lot of the OEMs today, they don't allow you to do two-way charging out of concerns for impact on battery life. But on the other hand, just like what Professor Gray and I do, we try to rethink the chemistry. We try to see, is the current chemistry the only way? Or if we have this vision for the future, that we assume that's the future we want, where there's a vehicle to grid, full integration, batteries are cycled several times a day and all the time instead of sitting there for 90% of the time, then what kind of battery do we actually want? That's kind of the job of academic, to think about these things. Every difficult question is an opportunity for us. Yeah.
And it's a real opportunity today. You have GM clearly announcing their new cars or trucks, which is going to be two-way. So I'm sure the warranty will need to adapt for that. So assuming this is the future and EVs can go two ways, what do you think that means for the battery design?
Can I ask a question to the investors about this? So I look at it from my perspective in Cambridge, where I don't drive very much, and I can't necessarily afford to have that large battery pack in my car sitting at home. But if I can use that to sell back, that changes it. So actually, people always talk about the degradation with the vehicle to grid charging. But I look at that as a potential way of making money and maybe justifying the bigger battery. And I know I'm contradicting myself because I also think of smaller batteries and sustainability. But I think there is an alternative perspective where you can justify your bigger battery by selling it back, but selling your storage basically.
I want to hear from Tyler and Claire on this one.
Claire, go ahead.
Sure. I mean, yeah, absolutely. I guess in my view, that's definitely what the future needs to look like. I mean, the first part of that is what I mentioned earlier, kind of the API that has visibility on the state of charge and being able to use a vehicle's battery as a flexible load entity. But the second part of that is being able to actually provide what you'd hope to be some form of resilience, right? And I think, I mean, even if you have, in theory, if you imagine an area or a concentration of EVs, even if you have small batteries, in each of them, if you're able to manage them as a set, and if we get better at predicting behavior and providing incentives to alter those behaviors, then that can be really meaningful, both for creating value for the EV owners, but I think potentially even more importantly for ensuring a low cost and resilient grid that we can grow and decarbonize.
One of the exciting elements of EVs and batteries as sort of the key component in an EV versus an engine is, I think we'll be able to actually design batteries for vehicles that are fit for purpose for a consumer's desired use case. So some folks will want that revenue generating asset that can sit behind the meter. It isn't highly utilized and can participate in the grid. Others might want the ability for a battery to really rapidly charge and discharge for performance purposes. So we're starting to see the OEMs kind of wrap their heads around that and begin to adopt software tools to help with those design decisions. I'd say still early days, but I think for almost a decade now, EVs have been from a product standpoint. Before Tesla emerged, it was essentially you were making a sacrifice and getting a product that was less performant than a combustion vehicle. I think we're right on the cusp of that beginning to change with all these new models coming out and the ability to do pretty cool things with an electric platform that were not possible with a combustion engine. So as an investor, that gets me really excited because that was largely not true for the past decade.
If anything, it creates a new way of using batteries all the time. Clearly, ride sharing was an application mentioned for having cars driving all the time and being used, and this could be a really nice way to avoid wasting the battery not being used. Cindy, do you have one more point you would like to add to this?
Yeah, I mean, I agree completely with what Clea and Tyler have mentioned. I just wanted to sort of add the comment that EVs are decentralized, and one of the things that we talk about is this major centralized grid with substations, and one of the benefits, I think, of both solar being decentralized and EVs being decentralized is that there are access points for both demand as well as resiliency, which gives consumers opportunities to make money, but also gives, I think, very, very importantly, on the grid resiliency side, if you think about how much money is spent on grid infrastructure to make sure it's resilient, to make sure it's significant and sufficient for the amount of load that's going to be there, the fact that we have decentralized batteries at many different locations on small, like localized nodes could be really effective as a stabilizer for the grid.
Thank you, Cindy. I'll take one more question from the audience. Too many to choose from, so I will actually be unfair and choose one that's short to read. Is there an analogous paradigm, and hard to say for me, for EV as far as standard protocols?
So I think protocols, like we've mentioned, safety is becoming a very critical element of the design of the vehicle. And definitely when you're going to fast charging and extreme fast charging, and you're sitting in a vehicle with an 800 volt system with 500 amps that are pumping into the vehicle, today you don't want to sit in this vehicle. Maybe you should go and have coffee, let the vehicle charge. So definitely new standards on the cooling, first of all, of the station, the cable, the connector to the vehicle, and then of course the active cooling of the vehicle and the pack itself. These are critical, and new standards have to come in place because the existing standards just do not support these rates whatsoever.
This has been an amazing session. I really enjoyed it, and I'm sure the audience enjoyed it. We can all agree that we're living here a bit smarter, if not a lot smarter, and more excited about the future of energy than when we came in. Please give a huge thank you to our panelists in today's session. It was a pleasure to have you join us, and thank you for the deep insight into the exciting world of energy transformation, or EX. And thank you to the awesome audience. Your questions were really good. You were engaged and keeping us on our toes with great questions toward the end. For entrepreneurs in the audience, feel free to reach out to our amazing investors, Cindy, Claire, and Tyler, if you are looking for investment opportunities. And investors who hope to learn more about leading research in charging field, don't hesitate to reach out to Professor Clare Grey and Professor Ping Liu. They are also commercializing their technologies through their spin-off startups, NioBolt and TieFast. Our industry partners, please keep tuned with Doron and StoreDot on their new progress and breakthroughs. Moving on, finally, we extend our gratitude to the top-tier event partners and sponsors who helped us get the word out about Energy Week 2021. Check them out, give them some love if you haven't done already. It has been my pleasure to host this session, and we are looking forward to bringing more outstanding content at the cutting edge of energy innovation to you in the remaining 2 sessions of TDK Ventures Energy Week 2021. So if you haven't already done so, please register for the remaining sessions to hear from other stellar guests on other important topics about battery and energy. You can use the QR code on this slide to go straight to the registration. Bring a friend if you can. Everyone is welcome. Tomorrow, you will be going to see world-class leaders from academia, industry, and VC to discuss various battery applications on energy storage systems, e-mobility, and grid integrations. The session is coming to a close, but this is important discussion. It should continue. Please scan these QR codes to join and contribute to this engagement on energy transformation, even after this event concludes. If you would like to share about Energy Week, feel free to use the tag Energy Week 2021 on LinkedIn. Thank you again to our guests, our audience, and we hope to see you all tomorrow.